So a second example of a data structure that we're going to look at is a table. So a table holds a collection of what are called keys, the things you look up, and associated values. So in this example here we have a little phone book. And the keys are the names of people, and the things we want to look up are their phone numbers. So the core operation in a table, as well as operations for constructing tables, will be looking up the value of a given key. So that's the main operation, and so a data structure should be designed to make that as efficient as possible. So we can use lists for this, and we've seen this example before. We can represent a table with key type K and value type V as a list of pairs, a list of KV pairs. So these are type. This is a type. So it's a polymorphic type for any type of key and any type of value. We can represent a table by a list of pairs. We saw this example before when we were looking at evaluating expressions containing variables. We had variables and values, and we used a standard function lookup to look up a given key in a table. Now you can only look up a key in a table when you're able to compare the key that you have with the keys in the table using the equality operator. So this only works for types K for which you have an equality. And the idea is that when you look up a key in a table that you hope to get back a value V. But of course the key might not be in the table. You might look up a name in a telephone book that doesn't have a telephone number. And so that's why we get, in this case, a maybe result. We get maybe a value. And if the key is not in the table, we get nothing. So one of the properties of tables represented in this way is that finding keys by searching from the beginning to the end is very slow. So if we have a big table, then on average we have to look at least half of the entries if the thing is in the table. And if it's not in the table, we often will have to look at all of the entries of the table. And the way that lookup works is it starts at the beginning of the list and works its way down until it finds what it's looking for. Now there's a much better way. It goes under the name divide and conquer. And that is if we were to start sort of somewhere in the middle, say here. And we're looking, let's suppose we were looking for the name Claesson. Then if the middle of the table has this name in it, then we know from here we have to search in the top half of the table rather than the bottom half. Now, of course, to be able to do it this way, to sort of split the table in half and decide, shall we look in the top half or the bottom half? That relies on the fact that the keys are in fact ordered. So these are all sorted in order, starting from A to in this case. But in general, it would mean that we have to have an ordering relation. So if we can put all the keys in order, a much better way of searching would be if we could divide our problem in half every time. We start in the middle somewhere and say, okay, well now we need to look only in this half table. So each time we look, we halve the size of the table. So that means on average the number of steps that we need to take is logarithmic in the size of the table, and not. So if the table has, well, let's say the table has 1,000 entries, then we would be looking we would hope to look up in the order of about 10 steps. Now, in order to represent tables in a way that allows you to do this, we can't just use a list. We somehow need to split the table up into the sort of middle point, the upper part and the lower part of the table. So each table needs to be represented in a way that allows us to easily access the bit in the middle, the upper table and the lower table. So here's a first stab at a data type to do that. A table of keys and values is something which joins together, this is a constructor, three things. The upper table, we'll call it for the left table here for now, the key and value that we have in the middle, so that would be Hans Nielsen's name and phone number in this case. The value would be the phone number. And the lower half of the table, or the right-hand part of the table. So it'd be a recursive data type involving two subtables. So that looks okay so far, but there's something not quite right with it. Can you see what that is? Well, the problem is that we have a recursive data type, but we don't have a base case. So we can only represent infinitely big tables. So we need a base case, and the base case is the case when we have a table that doesn't have anything in it at all. So eventually we get down to a table that is empty. So either we have a table which is the join of two tables with some middle point, or the empty table.